All right, so last time we introduced the notion of a limit of a function at a point, and we did a lot of examples trying to understand what limits are really about. And in this section, I want to show you how we can begin computing limits precisely. And so one of the main tools we're going to use is the so-called limit laws. And so we're going to assume that we have a function f of x and g of x, and some x value a. So a is a point on the x-axis, such that the limit as x goes to a of f of x and the limit of x goes to a, the limit as x goes to a of g of x, both of these limits exist. I want to assume both of these exist. So there's a number that f of x is getting closer and closer and closer to as x goes to a, and there's a number possibly different that g of x is getting closer and closer and closer to as x goes to a as well. And then remember, this just means C is in R, so C is a real number. Okay, so we have the following four limit laws. So first off, the limit of the sum of two functions, so f plus or minus g of x, is exactly what you think it should be. This is exactly the limit as x goes to a of f of x plus or minus the limit as x goes to a of g of x. And somehow this seems so apparent that it may not seem like a big deal, but it is. It doesn't have to be this way. This is telling you that limits of functions, of sums of functions, work the way that you think they should, as long as you know that both pieces actually exist. That's important. We'll do examples where if neither limit exists, where neither limit exists, but the sum actually does. So again, please don't forget that we're assuming at the beginning that the limit as x goes to a of f of x and the limit as x goes to a of g of x, both of these limits actually exist. Okay, so when they both exist, you can break up their sum in the way that you think it should. Here, you can do exactly what you think you should. If you have the limit as x goes to a of a constant times your function, then you can write this as c times the limit as x goes to a of f of x. You can pull constants out of the limit. Again, products work exactly the way that you think they should. The limit of the product is the product of the limit. So this is, I hope you can't hear that beeping noise. This is the limit as x goes to a of f of x times the limit as x goes to a of g of x. It's all good. And now the last limit is, again, exactly what you think it should be. Let's slide it down so we have a little bit more room. This is just the limit as x goes to a of the top one, divide by the limit as x goes to a of the bottom limit. And we are going to go ahead and assume that, let's say, assuming that the limit as x goes to a of g of x is not 0. We do have to add that assumption. Otherwise, we could divide by 0. So it may be that g of x is not 0 around a, but at a, g of x is 0. G of a, I'm sorry, the limit as x goes to a of g of x could be 0. Does that make sense? So g of x itself may not be 0 anywhere near a, but it may be that when you compute this limit as x goes to a of g of x that you get 0. And in that case, the limit law doesn't apply. Otherwise, the limit of the quotient is the quotient of the two limits. So let's look at two special limit laws. I actually need to make a little more space. I'm going to slide this down real quick, pardon me. So we'll slide that down. And I wanted to look at these two special limits with you. And we're going to try to evaluate them graphically here. Let's do this, and we'll draw a little line there. That's going to get messy. Hold on. So we'll make a line. There we go. And we'll do that. All right, so for the first one, let's think about what is the limit as x goes to a of just a constant c. Well, draw a picture and ask yourself, what does the graph of a constant function look like? You just go up to wherever c is. This is y equals c. And we'll just say a is right there. Who knows where a is? The point is, as x goes to a from the left or from the right, my function f of x is always c. So it makes sense to say the function f of x is getting closer and closer to c as x goes to a, because it's always c. So this limit you can see, no pun intended, is just c. Make sense? And then the other limit that we need is the limit as x goes to a of just x. And so let's write that one down. Let's graph the function. So here is my function x. Oops, and let's just pick a random a. We'll say here's our a. And so again, think with me. By the way, if this is a and if this point is a, then the point right that it's getting mapped to, you know, is the point. Think about it. It's just a comma a, because this is the function x. And so as x goes to a from the left or from the right, the function is getting closer and closer and closer to the y value a. And so this limit is just a. All right, so armed with those two limits, we can now work out an example. So let's do one example and then we'll end this video. So here we go. We've got this function, x cubed minus 4x squared plus 5x plus 2, and I want to compute the limit as x goes to 1 of f of x. So I'm going to work this out with a little bit of care because I want you to see the limit laws in play. So the first thing that I'm going to do is realize that the limit as x goes to 1 of f of x, which is this function, by limit law number 1, the limit law involving sums, I can break that limit up into a bunch of limits, a sum of a bunch of limits. So I can write this as the limit as x goes to 1 of x cubed minus the limit as x goes to 1 of 4x squared plus the limit as x goes to 1 of 5x plus the limit as x goes to 1 of 2. Yes, I could have done more, but I want to use these limit laws very carefully. So now in the next part, I say, okay, well, for this limit, I can actually factor out a 4, and I can factor out this 5. So let's do that. So I can write this as this line is equal to the limit as x goes to 1 of x cubed. Let's make that a little bit clearer. X cubed minus 4 times the limit as x goes to 1 of x squared plus 5 times the limit as x goes to 1 of just x plus the limit as x goes to 1 of just 2. Now, we can evaluate a couple of these. We know this limit is just 1 and this limit is just 2 because of the two special limits that we just did. So we can go ahead in the next line. I'm going to do those, but let's focus on this part. This function x cubed I can think about is just x times x times x. I'm taking the limit of a product of functions using limit law number 3. I can break that up as a product of the limits. And so I can write this if I want to, this x cubed, I can write this as the limit as x goes to 1 of x times the limit as x goes to 1 of x times the limit as x goes to 1 of x. So rather than write it out 3 times, I'm just going to cube it. And I'm going to say this is 4 times the limit as x goes to 1 of x, and this one is squared. And then we already said, well, 5 times this limit, you know you can just plug in the 1 and you get 5 times 1 plus this limit, you know you're just going to get out the constant, which is 2. And so now I get, well, the inside limit here is 1, so I get 1 cubed minus 4 times 1 squared plus 5 plus 2. So what is the 7 plus 1 is 8 minus 4. I get out that the limit is 4. So let's end this video here. Those are the limit laws, and this example shows you how you can actually use them to compute. Now, some of you that are paying attention would notice that, hey, if I just plugged in 1 at the beginning, I would get 1 minus 4 plus 5 plus 2, which is just 4. And maybe it feels to you like we're overcomplicating everything. Why do we need all this talk? Can't you just always plug in? The answer is no, you can't always just plug in. But in the next video, I'll tell you some situations when the limit is equal to the value of the function, which means to compute the limit, you can just plug in. That's not how we do it in general, but for special functions, you can. So let's end this video, and we'll pick it up in the next one.